Welcome everyone. Thank you for joining us for today's webinar, Verification Automation Using AI. I'm your host Neena Chandravli. Agnisis is a leader in electronic design automation, delivering solutions for complex design and verification problems in system development. This webinar will showcase how AI helps identify verification gaps, optimize stimulus generation, and reduce redundant simulations, leading to faster coverage closure. This session will go deep dive in how AI-driven verification solutions can analyze design specifications, RTL, and register descriptions to automatically generate UVM components, test scenarios, assertions, and coverage models. As a reminder, everyone will receive an email with instructions on how to review the PDF and recording for today's webinar. We will also be taking some time at the end of the webinar to answer your questions. So please do use the questions panel on your screen. Please welcome our presenter for today's webinar, Freddie. Freddie is an applications engineer at Agnisis and has 5+ years of experience in this field. Over to you, Freddie.
Thank you for that introduction, Nina. Hi, my name is Freddie, and in this session, we'll focus specifically on AI Square and how it automates UVM generation, coverage creation, and register-based verification directly from a specification. So here is our agenda. So we will look into what design verification it is itself, some of the challenges, and how AI Square can help. Then we'll dive into actually what AI Square is, so our complete automated verification system. We'll give an overview of what is generated by AI Square in this verification environment, and we'll also go into a quick demo showing how tests can be created using AI Square. So again, design verification. So again, the purpose of design verification is to verify that the design meets the system requirement and specification. So there's checks and verification done to check the correctness of protocols, interfaces, and there's different ways to do it. We have logic simulation, functional verification using models, and formal verification testing against coding models. As designs grow in complexity, the verification effort grows disproportionately. Usually, verification consumes 60 to 70% of total development time. So, what are the challenges of verification? So, one is the high cost of verification, both in time and in resources. So, usually, verification takes 70% of development effort is verification. And then to do this, you need different tools, different simulation license, and the cost of the computing power. Another thing of verification is the lack of man hours. So there's not enough qualified experience verification resources that allow you to create all these different tests and design. And then a lot of manual work is used translating design into test code. So from your test intent to your actual UVM design. So again, that could be error prone, tedious, and not really good use of time. Just design verification, there's also the need for a horizontal reuse. So verification at the end, again, you always have to go to firmware, prototype, and validation is needed. So typically, when we come to this, it could be that the source, there isn't a golden source that shares code. So people have, again, your architecture, but then you have your firmware team doing the different implementation. You have your DB team doing a different application. So when it comes to that, there's different environments, different languages, different focus. And then we also have vertical reuse. So that's just being able to reuse again your it's difficult to vertical reuse from an IP to SoC level. So what we feel is it's most importantly that engineers spend time on we use AI to kind of eliminates time on repetitive tasks and then do high value reasoning. So we said that verification takes about 75% time of the development cycle. So where does it spent? So it's spent in understanding the design intent. So you got about 10% there, creating the verification plan itself, implementing and defining the verification architecture. That's about 20%. And here we see that a good chunk of time is implementing and debugging the test. So that could take about 30% of the time. And then again, running regressions and debugging, and then reviewing the coverage of the code. So if we can, we likely want to reduce the amount of time that we are implementing and debugging this testing code. So that's where we have your AI squared. So what we're trying to do here is AI squared shifts verification from manual coding to specification-driven automation. So instead of writing your UVM components from scratch, what we want to do is give a test intent along with our, our register specs, and then let AI squared generate the rest. So here we kind of have a design of how AI squared works. So there's a drop-in and ready integration. So there's kind of a different step to how this model works. So the first one is document ingestion. So AI squared extracts semantic structure from, say, a Word, PDF, SmartDL, IPExact, or our own custom GUI, IDSCF. The next thing it does is it does knowledge representation. So it uses representation and causal correlations to establish concrete proofs for every assertion beyond just text. And the third itself is the bread and butter, the UVM generation. So using logic-driven and LLM-guided reasoning, AI squared generates standard compliant UVM test sequence. So here we're going from a philosophical shift from a manual effort into creating these UVM tests to passing into AI-assisted engineering. So let's kind of now take a look to what's created using this AI squared. So what AI squared brings to the table, uh, it generates the design components, again, the IP register logic, and then a wrapper module as well. It generates the complete UVM verification environment. So we get the reg model agents, coverage collectors. It has support for multiple different buses. So the majority of the AMBLE family, Avalon, TileLink, or your own custom if needed. Again, we can generate register sequences. The AI square can do it from the test intent, or we have custom sequence template that lets you do that. And you can generate custom checks as well. So AI squared treats verification as reasoning over knowledge. So again, here we have an example of our idea CF. It's just a implementation of how we can define some registers. You can see we give it a spec file, and then we can give it an intent. So it's generated test intent specifications. It understands the design intent, not just the behavior. So kind of what you want to do in your design. It handles ambiguity and contradictions contextually. And again, it's just freeing engineers from doing repetitive, mundane tasks to a more creative verification problems. So this is kind of an example of the AI squared. So we're giving it a test intent, in this case, in kind of a human language text. So again, what we're telling it to do is we have these registers that were created. So we want to program these registers. Again, then you could give it a more complex version. You say you want to program these payload registers, but then it should be given value should be at least a minimum one, and then the length should be greater than or equal to 46, but less than 1501. So again, you could give it multiple different parameters besides just from writing to the registers themselves, and then you could check for additional different busy bits, check values. So what we did here is we have this intent in human language. We fed that to the AI squared, and it automatically generated these UVM sequences. So now let's look into a typical block in SOC. So here we have the canonical block, so typical block in SOC. So everything here in orange is what is generated by AI square. So again, we have the register RTL block, of course. We have these bus interfaces, the register and signal interfaces, and the external interface, along with this RTL block wrapper. So traditionally, engineers would manually connect all these pieces, but AI Square automates this and the wrapper generation and verification connectivity. So here in blue, we have user app logic. So that's just anything that you want to attach to these registers. So later we'll show an example of how to generate all of these. So the register RTL block, the test for this user app logic, and how to integrate it all together using the RTL block wrapper. So next we go into the register RTL block. This is also generated by AI squared. So when it comes to the register itself, it's about 25% of the time is spent on the addressable registers. Again, registers do seem simple, but thing is, with more complex designs, you can typically have thousands to hundreds of thousands, and then later that might be changed. So for a register itself, you will need the RTL, but then again, to be used with different teams, you have different needs. So you might need C code for the firmware, UB and RAL for the UV teams, and HTML just to kind of make sense of what's being created. So a single change has to be translated in all formats to all teams. So we can do this using AI squared. And then here we just have a sample of defining register in IDSCF. So IDSCF, a collaboration framework, is our cloud-based way of defining registers. So again, you could give a register name, offsets, and define different fields in that register. And then from this, again, you could generate different collaterals like Verilog, UVM, SV, and register sequences. So now we'll give an overview of the AI squared generated verification environment. So here we have the generated UVM test bench. So what this snippet shows is the automatically generated verification environment. Here we're targeting the bus layer, the register IP layer, and the hardware application layer. In this IP verification environment, we generate all this environment from a golden spec and verify the design using inbuilt register sequence, automatic ones that we have, along with the custom ones and the ones generated by AI squared. So there's different components of this. So here we show the reg bus agent, and then what that does is converts the register level transaction to bus level, and vice versa. And then we have again the model updater that updates the route model through the tapper interface, so we can see here. And then again we so this is just kind of the high level test bench environment that we're creating. So again, diving a little closer to each component, here we're looking at the reg model. So again, the register model just represents the structure of a instance of each register block. And then this file again contain register files, memories, and hierarchical subblocks, so just different architecture. And then each model corresponds directly to the hardware and register. And so here we're showing that AI squared can automatically generate the reg model, again from our specification. Next up, we have the model updater. So again, the registers and hardware can be volatile, meaning their values can change due to the internal logic, not just the software. So to keep the UV and register model line in the DUT, we use the model updater. So whenever a hardware event occurs, such as a write or a state change, the model updater captures the updated value of the tapper interface and it mirrors it into the corresponding UV and register field. So again, we do this just so the register model always reflects the actual hardware state. Next up, we have the tapper interface. So the tapper interface plays a critical role in maintaining the synchronization between the hardware and the verification environment. Again, it taps or captures the internal values directly from the hardware registers in the DUT, and this is done just to ensure that the software model accurately reflects real world behavior. Next up, again, we have the component interface. So what the component interface here does is defines the hardware interface between the user app logic. So that's shown here in blue. and the wrapper block, again, which is created by AI squared. So it has the pins and signals through which the wrapper communicates to outside of the registers. So control signals, status outputs, or data path. So they can be monitored inside checkers to validate correct data flow and protocol behavior. And then next up we have again the automated bus verification. So again here we have the bus adapters, sequencer, and the reg bus drivers. Next up is the coverage collector. So AI Square enhances the coverage by automatically translating these LUTs defined on the register into functional cover points. So instead of having to manually write the cover groups, the AI Squared generates implicit cover points inside the coverage collector from the LUT definition. So again, just taking these laborious and menial tasks and using AI to automatically generate. And then again, we also have AI Square also has these register sequences that are generated based off the type of registers. So there's different sequences that are based off the register access on the hardware side or on the software bus side. And then if any special registers are being generated, there's also support for those. So any lock registers, registers that support aliasing or shadow registers, constraints on register fields, or FIFOs. So again, based on the type of register itself, we have these automatic register sequences that are generated. Next up, we're showing coverage collector using inline LUTs. So we have these inline lookup tables, again denoted by inside these curly braces, and we can see how the cover groups are generated uh, using these inline lookup tables. Additionally, we do support cost coverage. So again, it's denoted similar here, how we have it using these enums. And then with additional properties, we can see that we can also support cross coverage. So AI Score will generate this cross coverage automatically, and this ensures the combination of states and air conditioners are validated without manual cover group configuration. And then additionally, aside from AI Squared itself, we have support for custom sequences. So we give these templates where engineer themselves can write their own set of sequences using these custom commands we have. So there's different things that can be done here, different levels of support of hierarchical sequences, use of structures for UVM, use of fork join constructs, and supporting different conditional statements like if, else, for, and while loops, and support for randomization and constraints. And then now we're looking into the output directory structure of what's generated in this verification environment for AI squared. So again, we have this output directory. Aside from that, again, this is the user application logic. So this is what you as a user would generate yourself. Aside from that, everything else can be generated again through this AI squared. So you have the DUT, you have the UVM register model itself, the coverage collector, the user-defined sequences, the register interface, and the checkers. And then in this ARV is where the AI-enabled tests are. So you have a directory called AI sequences that are generated again based AI squared with that test intent. Register sequences. So those are automatic based on the register definition itself. And other things that we talk about, like the bus agent, the model updater. And then additionally, we have make files for different simulators. So it's kind of plug and play configuration. So all you have to do is run the make file to see the coverage report that it generated. So here we have a demo design itself. So we have this design in our CF defining some registers. And then we have this state machine again that has some transitions in it and some output components. So we'll go into a quick demo of IDSCF, it's AI squared itself.
Okay, for the demo, we have a very small design just to prove the concept. we have a register block, which is represented by these three registers. And then it is talking to a state machine, a very small state machine. And it also has a couple of ins and outs. Um, Now, this is represented in the CF, which is our collaboration framework, in a GUI form. This is the GUI form where we have all the registers, and also in system RDL. Here are the here is the RDL representation of the three registers. This could be as complex as you want. Um, and notice that currently the output is empty. There's nothing in the output directory. And the core logic that you want to connect to the register is in the app logic. And that has the details of the design. The design itself has been specified in a spec document, which is this is the specification. This could be as elaborate as you want. Now, what we're going to do is, first of all, check the spec quality, whether the spec is good, it's good or not. And then we're going to generate from that, we're going to generate the output, the sequences. So checking the spec quality, I click on this and it goes through and connects to our local AI engine, and it's giving issues that it found. We're not going to go into all the issues, but let's go ahead and then generate. But if there were issues, then it would point them out right here. So in the generate phase, it is basically reading in the input spec, parsing, building a knowledge graph, and then generating all kinds of FSM and tests, and then creating the entire UVM environment along with the agents and the sequences, and then we can take a look at it. Now let's go to the output directory. Yeah, in the tool, there is the output directory, and notice now that it is filled. It's got all the things. Let's go into all the details. Let's see, let's say, where is the, yeah, and we can go in the normal Linux as well. Let's look at the timestamp. It was just created. Okay. And then let's run the simulation on the generated file. Actually, before we go to the simulation, let's look at the sequence that got generated. So this is the AI sec directory, is where all the sequences are. There is the RAL sequence. And then there are sequences for the various inputs. Yeah. And they're all connected together by a master sequence. Yeah. And this is basically being generated from by reading the input specification. And now let's run the simulation. We're using Questa, thanks to Siemens. And now it's going through compiling everything and running all the tests, and then the coverage, and it's merging all. I mean, we're not running too many times, but here is the coverage is also has also been generated. And now let's look at the UCDB file and look at the coverage. So the cover groups, incidentally, were also generated by the AI. And so now look, that based on the specification, we're getting 100% coverage. So I know it's a very small design, but I think it proves the point that we're doing everything using AI in a very controlled sort of way. Thank you.
So that was a quick demo of showing AI squared in action. And here we can see again the coverage report. So again, using these AI generated tests, again, just from the test intent, no need to any of the manual coding. We can see that we do have across the board this accurate 100% coverage. So again, the benefits I think outweigh themselves. So when it comes to manual coding, there's always needs to update, and then you have to update across the board, the Verilog, the UVM RAW, the sequences, and the entire environment. AI squared, there's no need to update because everything is generated again by the test intent. So if anything needs to be changed, it can be changed again using AI squared. So what benefits you get here? You have reduced manual change, faster design iterations, higher consistency, improved productivity, and hopefully better first pass silicon success. Another thing that could be useful is if you're new to the UVM verification, you can create the complete UVM based verification environment without the need of too much verification or UVM experience. And then if you're an advanced user, again, a good kickoff point. So no need to manually create the environment. You don't have to work manually on the sequence themselves, and then you have more time to work on more complex areas of the chip. So that about sums up what we want to show here in I Square. So again, a little more about us is we feel like when it comes to this hardware software interface, uh, uh, we're leaders in the aspect of complex design and verification. So if you have any questions regarding I Square, you want to see the design more, you can reach out to us at support@agnisis.com or our contact page. And we'll also be at DVCon US if you want to see a live demonstration of this AI squared. All right, thank you. I'll pass it back over to you, Nina.
Thank you, Freddie. We do have some questions for you. Just a reminder to our attendees, if you have any questions about today's webinar, please enter them in the questions panel. And now on to your questions. The first question is, how can users input their specification into AI Square and what input formats are supported?
So AI squared supports multiple different input specifications. So the specification can be created in the IDSCF, our collaborative framework. It's a real-time template-based environment. And then they can be defined there. And then additionally, with the use of the collaboration framework, you can also capture in different languages like System RDL, IPExact, IDS Word, or NG. And for the application logic, for those sequence tests that we have, that can be done in Word documents, PDF files, or natural language and text based.
Okay. The second question is, how does AI Square help improve coverage closure and reduce verification bottlenecks?
So AI Square automatically generates coverage models, cross coverage, and constraint driven sequences from the spec. So this accelerates the coverage closure, reduces manual effort, and ensures that the verification completeness is aligned with design intent given.
Okay. Third question is, what role do knowledge graphs and vector databases play?
So the knowledge graph captures the structure relationship between different components like the register, field, interfaces, and behaviors, and the vector database enables the semantic search or the contextual understanding. So together they allow the system to reason the specification rather than just process a static text. So again, just understanding it instead of reading it in altogether.
Okay. The next question is, what does drop-in and ready integration really mean in practice?
And what we're saying in these terms, it means teams can bring in their existing specification, structured or unstructured, and directly into the platform itself without having to do any manual rewrites or any manual efforts. So the system automatically takes in structures and transforms the content into an automation ready format. So it's kind of easy plug and play without adding disruption to current workflows.
Okay. The next question is, how is UVM generated using LLM guided logic?
So yeah, as we saw before in that diagram, the system combines rule-based verification logic with LLM guided reasoning, and that's to generate that static light UVM environment. So this is make sure that the output is deterministic and aligned with the design intent, and not just a generated text output.
Okay. The next question looks similar to the first. Is the test generated from original spec or from the user-defined spreadsheet that describes tests?
So it's using both. Again, we have the specification for the register itself, and then additionally we'll have that test intent. So that in this case we showed it a text-based file, but again it could be a Word document, PDF, or a different text-based format.
Okay. The next question is, in what format the design intent is extracted from the specification? Is something that can be read or reviewed?
Could you repeat that, Neil? Sorry.
Yeah. Uh, the question is, in what format the design intent is extracted from the specification? Is something that can be read or reviewed?
Yeah, so the test intent again can be extracted again from the Word doc, a PDF file, or natural language. So when we say a text-based format, that's what we showed in terms of what we wanted the test to do. In PDF files, again, that could be different manuals. So if you have manuals for certain device architecture, those sequences can be extracted from there as well.
Okay. The next question is, what is the average reached functional or code coverage of generated test cases?
So far, like we showed, we've usually been close to 100%. So if you don't get that 100%, again, you could just go through different cycles. You can update the test intent or update the different tests, but usually we've been reaching close to 100% coverage.
Okay. Um, I'm not clear on this question, but requirements and generated test coverage results.
So if we're talking about requirements of the tool itself, so this tool itself uses our own proprietary LLM model, but then it can be run on premises. So if you're talking about like hardware spec requirement, we can talk privately. So you can send us an email. What was the second part again, Ina?
One was requirement, other was generated test coverage results.
Yeah. So again, like we are saying, here we showed one that got 100% coverage, but usually it's either near that, or close to that. And again, it can be done just going through a few reiterations.
Okay, so these were the questions. Thank you everyone for joining us for today's webinar. As a reminder, everyone will receive an email with instructions on how to review the PDF and recording for today's webinar. If you have any questions or would like to view downloads, we invite you to fill contact us form at agnesis.com or send us an email at support@agnesis.com. You can also meet us at booth 111 at DVCon US to explore on AI solutions. Stay safe and we'll see you next time. Thank you.